to meet you. We have a new video and new problem. Let's go. Our objective is to prove these inequalities. If we prove these two inequalities and we prove this proposition, then we have solved our problem. How? Because if we have the f of n equals square of n plus square of n plus 1 plus square of 1n plus 2 and plus 8, then and if we prove this proposition, then f of n squared is between 9n plus 8 and 9n plus 9, and these two are successive integers, and because 9n plus 8 is not a square, there must be the first square on the left. 9n plus 9 can be is a candidate square, but if it is not, we will find the first square here, and it is of course k plus 1 square, and then we have f of n between k and k plus 1, because this inequality is strict. And then we can say that f of n equals 9 plus 8 equals k, because square of, if we put it here square, it is between k and k plus 1, and we have solved our problem. Let's go and prove these results. Let's prove first this the proposition 1. In the proposition 1, we have the mean of the squares is smaller than the square of the mean, and this is because function g of x equals square root of x is concave, because second derivative of x equals minus x minus 3/2, which is negative. And if we apply this result to our problem, we'll get this inequality, because we have square root of n plus square root of n plus 1 plus square root of n plus 2 divided by 3 is less than square of the mean of these number at under the radical, and the mean of the numbers under the radical is n plus 1. This implies that the sum of squares is smaller than 3 square root of n plus 1, which equals square root of 9n plus 9. And this is the first inequality in the theorem. Now we need to prove the second inequality of the theorem. If you remember, we have the inequality at the right hand side and the inequality at the left hand side. We have f of n minus 3 square root of n equals minus sin plus n plus 1 minus square of n. This equal to 2 divided by square of n plus square of n plus 2 plus 1 over n plus 1 plus square root of n. And this is greater than 1 divided by square of n plus square of n plus 2 divided by 2 plus 1 because we replace this quantity by this one. And look here, we have the mean of the squares, then it is greater than 2 pardon, and it is greater than square of the mean of these two integers, which is n plus 1 plus and this equals 2 divided by 2 n plus 1. So f of n is greater than 3 2 n plus 1 square root plus 3 square root of n. And we should prove that this quantity, it is sufficient to prove that this quantity is greater than square root of 9n plus 8. And to do this, I will compare the squares of these two quantities. Divided by 4 n plus 1 plus, this is the square of this, plus 9n plus double product 2 multiplied by 3 divided by 2 multiplied by this, it is sufficient that it is greater than n plus 8. And we can eliminate this term and just compare the rest. And here we can get rid of this, and it is sufficient to prove that plus 9, here we have 9, and is greater than 8. And this can write it as and it is sufficient to prove that this quantity is greater than 8. And here this quantity between parentheses is greater than 1 minus n. And this quantity we can prove that it is greater than 1 minus and we can prove that by using we can prove this inequality by using the mean value theorem, that this quantity is greater than this one. And here we can get rid of this 8, and then it is sufficient to prove that this quantity is greater than 0. If we take n greater equal 3, we will find that this quantity is true for n greater than 3, because let's verify 4 multiplied by 9, which is minus 9 multiplied by 3 minus 9, 36 minus 27 minus 9 equal 0. Then we have proved the left hand side inequality of the theorem. Can live for n equals 0, 1, 2, we can verify manually that racine of n is square of n plus 1 is square of n plus 2 is equal to we can verify it manually. For proposition 2, we have here two inequalities. The first, we can prove it using the mean value theorem, And this inequality is interesting when x is near 0. Uh, Second inequality can be proved directly. That is, for the second inequality, we have multiply this by this, so that it gives 1 minus x squared divided by is equal to x squared over 1 plus x, and this is non-negative. For the first, as I say, we have to prove mean value theorem. We apply it to the function g of x. Uh, we have shift the derivative of x of g. First derivative is uh, if we apply the mean value theorem, we have equals g of 0 equals 1, and it is equals to uh, for some c in 0 x interval, open interval 0 x. So we have g of x equals 1 minus 1 divided by 2, and it is greater than 1 minus. And this because we have 2 multiplied by is greater than 2. And here we finish the proof of this proposition. To prove proposition 3, we'll use modular arithmetics. So in Z9z have 0 square equals 0, 1 square equals 1, 2 square equals 4, 3 square equals 0, 4 square equals 7. It's not necessary to compute the squares of the other because, for example, the square of 5 is the same as the square of 4 because their sum is 9. So this implies that uh, x squared can be 0, 1, 4, or 7. 9n plus 8 equals 0 mod 9, and h is not listed here. So now to square modulo 9. Now my proof came to its end. Thank you for watching.